Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello. Hi. Alan is my name, and I'm here for chemistry lessons. Senior 6 students, welcome back. I hope you're fine and still healthy. So we are in for lesson 5 on our topic chemical kinetics and unit rate laws and their measurements. So basically this lesson we're going to be looking at the overall order of a reaction and the reaction mechanism. So when I talk of the overall order of a reaction, we already looked at calculations involving overall order and how to get the overall order. For instance, in the previous calculation, you looked at getting the overall order by getting the order with respect to reactant A, which was 1, and order with respect to reactant B, which was 2. So we add them. So in this case, we are going to be looking at if you have, for instance, an overall order of 2, what does it imply? It can be 1 plus 1, which is 2, or 0 plus 2, which is 2. So such a forms are what we are going to be looking at, and the examples of reactions which they fall onto, and we look at their reaction mechanisms. So as I had said, the focus will be on examples of reactions in each order and illustrating their mechanism. In that case, our key terms are a pseudo first order reaction. Pseudo meaning false. Then we look at reaction mechanism and the rate determining step in the reaction mechanism. And as you've seen the word pseudo, I hope that is not new to you. If it is new, you have a second to actually look for it in the dictionary. I'm giving you a second to look for it in the dictionary, because we shall not go deeper into the English meaning, but the chemical meaning. And the objectives are you to describe the possible forms an overall order may take and give a few examples in each case. As I said, like if you have 2, it can take 1 and 1, or it can take 0 and 2. So in each case, can we suggest a few examples? Of course, basing on the knowledge that we shall have covered, I'm pretty sure you'll be competent enough to suggest a few examples. Then we explain steric hindrance and how it actually comes in to bring in a different reaction mechanism. So that is what we shall look at, and those are the specific objectives I want you to pick by the end of this lesson. A recap, you already know this stuff, but again, to a new student who is just coming, this is crucial information. You will need it, so if you're joining us, please remember, for a second order reaction, the rate is directly proportional to the square root of the concentration of that reactant, if you're using A, for instance. Then for a first order, rate is directly proportional to the concentration of that reactant. That's why we have a 1 here. Any number power 1 is always that number. So rate is directly proportional to the concentration of that reactant. And for the 0 order, any number power 0 is always 1. So for a 0 order, the rate is independent of the changes in the concentration. So we're going to see different forms and give different examples. Here we've been just saying a reaction A plus B. But in this lesson, we are going to use specific examples since we understand what these laws imply. That is a recap. If you're joining us, please know that knowledge. So let's start with for an overall second order reaction. If you have an overall second order reaction, 3 possible forms. But before I reach on the forms, first look on the slide, I explained something there. So if you look at this reaction, A and B as our reactant, for instance, the overall should be a 2, indicating the order with respect to reactant A plus the order with respect to reactant B, X and Y should be a 2. That is overall. Is that point taken? When we talk of overall, get the order of one reactant, add it to the order of another, then get the value as 2. So with that understanding, what are the possible forms? These are the forms, just 3. Either X is 0, because 0 plus 2 will get 2. Then when X is 0, Y automatically becomes a 2. If we flip the coin, X becomes 2, then automatically Y will be 0. Or you can have 1 and 1. And you know when we have the order as 0, what that implies? Changes in the concentration does not affect the rate. And when it is a 2, double the concentration, the rate increases by a factor of 4. So, but in most cases, second order overall reactions take a form of X equal to 1 and Y is equal to 1. What do we mean? This is what we imply. The two reactants involved in a reaction affect the rate of a reaction. We don't have a reactant which its concentration, when it changes, then the rate isn't affected. For the case of X is equal to 1, for this case, X is equal to 1 and Y is equal to 1 means both of the reactants are affecting the rate of reaction. And here is the example, hydrolysis of primary alkyl halides. We are going to see the detailed mechanism when we reach on the part of the mechanism in a few slides ahead. So what happens exactly in here is when you bring OH, which is a nucleophile substituting a bromide, I'm pretty sure you actually looked at these reactions in your Form 5 organic reactions. But let's make a quick go through of it. So when you bring OH as a nucleophile substituting Br, these two must collide up together to determine the product, which is maybe OH. And this experiment was followed up, and they used silver nitrate to determine the presence of bromide set free. And this is the cream precipitate that comes as a result of this reaction. So the point is rate is dependent on both OH and the alkyl halide. So this is a second order, but each reactant has an order of reaction as 1. So the sum becomes 2. Another example is that for iodine and hydrogen, as you can see. So that is the category of this overall second order reaction. Now let's go to the first order. Overall, that is a crucial part. Overall meaning the sum of all the orders in a reaction should be equal to 1. Same way, X plus Y should be 1. Similar permutations, indicating for us to get 1, you either have X as 0, Y as 1, or X as 1, Y as 0, or halves in each case. But in real experimentations, mostly the overall first order follow this category. You only have one reactant. Because if you bring in the second, then it is highly likely going to cause an effect. So let's first pause on that, causing an effect. Let's first pause on that. We shall look at it just in the next slide. So let's look at this reaction, A giving to products. Either X or Y should be 1. And that gives us the overall order as 1. You can suggest a few examples where you only have a single reactant. Suggest. What do you think? Think from your chemistry of S1, S2, S3, S4, S5 up to now. You should be having a quick example there. A minute? Yeah, you have a minute to go to think of it. Okay, so these are the examples. You see, unique character, it is a single reactant, and it is a characteristic of most of the decomposition reactions. They are breaking, all disintegration reactions. You see, they are breaking, like decomposition of hydrogen peroxide. This is the setup. You see the highlighter. This is the whole setup for its measurement. So such are the examples. You see the rate is only depending on the concentration of the single reactant you have. Now, we come to the word pseudo first order. Remember what I told you at the start? Get a dictionary and find the meaning. If you couldn't easily get a dictionary, then let's get the meaning from here. Pseudo meaning false. It is a false first order. It is not real first order by the characteristics we've just looked at, but it is a first order reaction. So let's look at this in details. Hydrolysis of ester. What do you need? You need water, since this is hydrolysis, indicating we are adding water. This is the ester. It is a methyl ethanoate. You may wonder what are esters. You know, you eat mangoes. Mangoes are full of esters. Most of the markets in Kigali here are full of sunflower oil. It is just having a lot of esters in it. So we eat esters, though we don't say this is ester or what, but we eat esters. So you have this methyl ethanoate. It is an ester. It is undergoing hydrolysis in presence of the acid as a catalyst to form ethanoic acid and methanol. So what do you notice? We have two reactants, ester and water, indicating by our second order expectation, this rate of reaction should be affected by both ester and water. Do we see that? Because we have two reactants. Since they are involved in a reaction, then they are supposed to affect the rate of reaction. This is what would be expected. Of course, some would also ask, what about the catalyst we are having? Yeah, the catalyst is there, but because the catalyst remains unchanged, so it does not really bring a greater effect in here. So this is expected. But do you know what results have shown? Again, I stress this point. Orders of reactions are obtained experimentally, obtained from the data from the experiment. You just don't look at the equation and say it has a first order or a second. They must be experimentally done. So experiments show that for this reaction, it is actually a first order with respect to the ester. Water, the changes in the concentration of water has no effect on this rate of a reaction. But it is a reactant, it is there. So this is what we call a pseudo-first order. It has two reactants. It's expected to be having both reactants affecting the rate of reaction, but it's only one, which is an ester affecting the order of reaction. So the question is why? Why isn't water affecting the rate of reaction? I will give you the answer, but after you've tried, I give you a minute. Let me help you and give you some direction. You remember the principles of chemical equilibrium? When you have water as a reactant, what happens to it? Now, I want you to pick up that knowledge and apply it in here. Pick up that knowledge, the knowledge of chemical equilibrium, and it's me who went through with you. So bring that knowledge over here. Okay, so hope you've gotten the reason. Now this is the reason. Remember, water as a reactant, it's normally in large excess. You know we are surrounded by water here, so indicating however the amount of water you want, you would always get it. Water is not a limiting factor. It is always in large excess. So in that way, when you consider the amount of water in regard to the concentration of the ester, the amount of water is excessively larger. So it is too much. And as being too much, it does not affect the rate of reaction. So the rate of reaction is only affected by the ester, making it a pseudo first order. It is only one reactant affecting the order of reaction. So pseudo first order reactions, if you have one reactant in large excess compared to the other, then the one in limited amounts alters the rate of a reaction. A quick lesson check. Quick lesson check for you. Yes, today you must really understand something by you doing it. So suggest a few examples of reactions which would undergo pseudo first order reaction. A trick, look at your organic. Which reactions in organic involve water as a reactant? And which reactions in physical involve water as a reactant? Okay, let's see what you've obtained. Show me. Of course, yeah, share with a friend and see if you got similar responses. I'm not saying exact, but similar responses. So here the example is hydration of methyl iodide. Again, I think you see we are involving water because water, wherever it is, it's always in a large excess. We are surrounded by water. It's not like a mango. You get mangoes once in a while, but water is everywhere. So because water is in large excess, its concentration in a reaction does not change a lot. It remains almost constant. So that is also an example. However, do not cram that it will always be a reaction involving water. We also have some reactions not involving water. Check it on the slide. The reduction of bromate 5, this is bromate 5, using your knowledge of group 7. So in presence of hydrogen ions, it is reduced to bromine and water. So from this, because the concentration of hydrogen ions and bromide ions are far greater compared to the concentration of bromate. These are the concentrations here. You see? This is 1, this is 0.001. This concentration is far greater than this concentration. The end product is these two reactants are not affecting the rate of reaction. So the rate is only affected by the bromate ion, making it to be a pseudo first order. False. It is not entirely a first order, but because of these factors, high concentrations regard to the other, it brings in the falseness. So that is it, and we can quickly look at the zero order before we can conclude up. Zero order, zero, any changes in the concentration does not affect the rate. Experiments, again, this is an example, decomposition of ammonia. Look at the first experiment setup. The concentration of ammonia was doubled, was increased. Rate remained constant. Look at the second setup. The concentration was decreased from 0.4 to 0.2 to 0.1. The rate remained the same. So for zero order, however much you alter the concentration, the reaction will keep on occurring. It will keep on occurring. So those are the different forms in which a reaction can occur and the examples of reactions. At least now you are informed of the reactions and how they occur. Again, I repeat this aspect. Such a knowledge is helpful in production of medicine, to know when how long the medicine will last in the body, in the production of fertilizers, to know how long, for instance, if I apply NPK, it will last in the soil, and so on and so forth. So let's go to our objective 2, reaction mechanism. Reaction mechanism and rate determining step. When we say reaction mechanism, what do we imply? Since you've already looked at organic, you perfectly understand the reaction mechanism. But some someone who is also attending with us this lesson, when we talk of a reaction mechanism, we are meaning a step-by-step approach, step-by-step way in which reactants form products. What do they exactly go through? So in a reaction mechanism, two crucial things are involved. One, intermediate stage or step, then intermediate species, which we call transition states. Let me bring this maybe to the real life in here. From the childhood to death, maybe when someone is around 70 years, 0 year to 70 year, or 70th year. What will happen? There are stages you go through. You go through childhood, then you go to adolescence, then you go to young adult, then you go to adult stage. Those stages are the ones I can compare with the intermediates in a chemical reaction. Let's see an example here. Hydrolysis of a tertiary alkyl halide. So, look at this. You have this as a reactant, and it is to form a product. Hydrolysis, we are adding OH. So we are making OH substitute a bromide. In this way, you will break a bond between carbon and bromine, then connect a bond between oxygen and carbon to form a product. So, what do we see? What do we see? The reactant must break to form an intermediate. The intermediate must combine with other forms of the reactant to form a product. But in this whole reaction, there is what we call a crucial stage. Okay, in real life, again, a crucial stage would be maybe the adolescence, where someone is coming to discover who they are, if they are girls, coming to develop the breasts and knowing that such a things are for girls, then for boys, such a things are for boys, such a stage of discovering. So in a reaction, it is not discovering, it is what we call a rate determining stage. It is the stage or the step that determines how fast a reaction will occur. If it goes slow, then the reaction will be slow. If it is very fast, then the reaction overall will be fast. Similarly, you normally hear this statement that the strength of a team is at its weakest point. However much bigger you are, but if you have that weakest point and someone discovers it, they will always win you because of your weakest point. Similarly, in the chemical reactions, as you see on the slide, for this reaction to occur, there is something that must be overcome for it to occur. That is the slowest step, which is normally step 1, and that is the rate determining step. When that step is exceeded, then the reaction becomes fast. So what is a rate determining step? It is the slowest step in all steps of a reaction. And it is characterized by two things, or it is determined by two things: steric hindrance and reactivity of the active site. We shall not go deeper into the reactivity of the active site, but let's look at steric hindrance. When we talk of steric hindrance, what do we mean? So we have these three classes of alkyl halides. A primary, because the bromine is attached on the first carbon. A secondary, bromine is attached on the second carbon, and the second carbon is surrounded by two other carbons. And the tertiary, the carbon with the bromine is surrounded by three other carbons. You see the examples. So what happens with steric hindrance? You look closely. This is the primary. You can see the black carbon illustration in here. This is the methyl group. Then these are two hydrogens. And this is a bromine. This is a bromine. You see some slight black part, which is carbon. This is a methyl group, and the methyl there, and the hydrogen. Then this is surrounded by methyls, as you see it here. So, for the primary, it is easy to access this carbon. You can even see it. So the incoming OH easily attacks the carbon. For the secondary, you can see some bit of the carbon, black carbon inside there. Look at my highlighter. So even the reaction is highly likely to occur. But for the tertiary, you see you can't see any carbon. These have shielded the carbon which is inside. So the incoming OH cannot go there. What happens for the reaction to occur? The carbon Br bond must break first. So this becomes a rate determining step because without this bromine breaking, the reaction will not go on. On the other hand, because, as we saw, attack can be possible due to easy access to this carbon, it will attack as the bromine bond breaks. In other words, for the primary, it's you give me and I let go. For the tertiary you must first let go for me to take. And all that is because of the steric hindrance. For the secondary, it is in between. And in that way, here, the reaction mechanism differs from this reaction mechanism because of that steric hindrance, bringing about different rate determining steps. In conclusion, this is what happens. You've already gone through this. I'm pretty sure of that, but let's go in details and look through each. So for the primary, hydrolysis of primary alkyl halide, the rate is depending on both the OH and the alkyl group. In other words, before this comes, this will not break. But for the tertiary, it will first break. So the rate is determined by the amount of the alkyl group. The OH coming does not have an effect on the rate of a reaction. And that is it. You can see the order from tertiary to the primary with the rate increasing. Thank you very much. I can't live without giving you an exercise, and that's the exercise. Please stay safe. I want to see you in the next lesson. Bye.